So, like others had mentioned, we kind of came to this field actually when some of our atomic physics colleagues came to us with this old problem, which was kind of asking the question, what is the maximum reflection that you expect from a single atom? So, as we heard, if you could focus a laser perfectly on a single atom, what would you expect? And I think there had been kind of a debate. And the idea is that basically if you think about the emission as an incoherent process, you guess that the answer would be 50%, because say basically just half goes forward and half goes back. But if you do the fully coherent calculation, as we've heard, you predict that there should be interference that will destructively interfere the forward scattered light and constructively enhance the backward scattered light. So in a fully coherent calculation, you project this 100% backscattering. And I think, as we've heard in, I guess at least the record in atomic physics had been kind of 10 or 20%, which is amazing because you're focusing a laser on a single atom, but it doesn't kind of answer the question of 50%. And so like the others, we had this idea of trying to do this in superconducting circuits, and unbeknownst to us, NEC was also working on this problem, so they got the results first. But we were also working on this, so the basic idea that we have this transmon qubit seen here with very stubby interdigitated capacitor in a superconducting transmission line. So the light color here is all aluminum and the dark is the substrate. And the magic here, as also been mentioned, is essentially that with these superconducting waveguides, we can confine the light very, very strongly to deep subwavelength dimensions in 2 dimensions. And that allows us to get this very strong coupling, even in a propagating or an open system. This was the basic first result. So here we're looking at the transmission in power past the artificial atom as we scan the probe frequency. And you see, in this first device, we get kind of 90% extinction, and one of the nice things is just with this simple network analyzer measurement, you can really read off basically what the coupling strength is, which is the width of this peak, and the residual decoherence, so the ratio of any other decoherence, like loss into other channels or dephasing. The ratio of that to this coupling is just the residual peak here. So here we had some extra dephasing, but in later measurements we've gotten 99.6 by making the qubit better. Now there's kind of a trick here, which is, so if you're a circuit person, I mean, you could also look at this and say, this I would expect if I just had an LC oscillator shunting my transmission line. So what's the difference here? Why do I claim that this is a qubit? And one of the first things that I can do then is actually just look at then the power dependence or saturation. So if I had an LC oscillator, that's a linear system, so the reflection should be independent of power. But if I now drive this system harder, so if I just crank up the probe power, I see that basically this transition saturates. So this is kind of a first indication that I have something other than an LC oscillator. And yeah, so you can see this is the magnitude, this is the phase with the fits. We can explain it quite well. And if we just take a line cut here and plot it as a function of power, we see nice curves like this, like we've always seen. So this is blue is this device with the 90% reflection, red is this the newer device with 99.6% reflection. But you can see that we get this very strong saturation of the transmission, and the simple explanation is that if I imagine that I have this 2-level emitter, well basically you can only reflect a single photon at a time, so if I probe it with much more than a single photon, basically everything just goes by. And just as kind of, that's kind of the story, but I can say if I just estimate, I can basically calculate how many photons are in my probe beam, and if I do kind of, photons per qubit lifetime, I get 1 photon should be here, right in the middle of this saturation curve. So we get this idea that we have this strong saturation that's happening at a single photon level. Now, we and other people realized that this strong single photon saturation could actually be kind of useful and put to some purpose. And that's one experiment where we did making a kind of device, well, it's really the same device, but an implementation that I call a quantum state filter. So what do I mean here? So if we look at this device, so again, now I have my qubit and my open transmission line. So I saw that we get this strong reflection, but if you do really the calculation, the theoretical calculation of the state that's reflected and transmitted. And for instance, we were kind of inspired by work by Derek Chang, done here, I think. You know, the idea is that, so I put in my coherent state, my completely classical state out of my generator, and that has some Poisson, you know, Poisson distribution of Fock states, right? Now, if I look at the reflected signal, again, because I have an artificial atom that can only reflect one photon, what I predict is that the reflected state should only have the 0 and 1 photon component. And this is a bit cartoony, but I also get that then, therefore, in the transmitted state, I at least suppress the 1 photon state, right? And so why do I call this a quantum state filter? Well, the idea is, you know, what does a filter do? If this was an LC oscillator, you know, a regular frequency filter, the idea would be that I could kind of accept or reflect the frequencies that I want, and then I can reject, or say in this case, transmit and kind of dump the frequencies that I don't want. You know, what am I doing here instead? I'm accepting the part of the wave function or the part of the quantum state that I want, and I'm dumping the rest. Well, more generally, what's kind of interesting about this is, at least theoretically, here I have a device where I have a completely passive circuit, but it can take the signal from my generator that's completely classical and convert it into a non-classical state, which then could be a resource for quantum information. So I think that's kind of an interesting idea. So we wanted to set about and see if we could really prove that this is what was going on. So how do we do this? Well, there's many ways you could do it. One way to do it basically is to look at the G2 function, so the photon-photon correlation function. This is a very standard technique from quantum optics, of course. So the idea is that I have my qubit down here, I can bounce the probe signal off of it, and then look at the reflection, and then I take the reflected state, and I put it into a microwave beam splitter. Andreas's group has put a lot of effort into making their own. We just have used, in this case, commercial parts, so this is just called a microwave hybrid. So it's something we can just buy. So we put it on a microwave beam splitter, and then we get the 2 output ports, and then we look at correlations. Now the trick is that, you know, in general, there's a lot of work on single photon detectors in the microwave, but in general, they're not any kind of technology. So we can't measure directly photon-photon correlations, but what we can measure is voltages. So we have these microwave voltage amplifiers. We can measure the quadrature voltages, and then you can show that by measuring higher moments of the voltage, in this case a 4th moment of the voltage noise, you can actually get out the actual G2. And just to say, I think these kind of microwave, higher moment measurements of microwaves and looking at G2 were done first in the early 2000s at Yale and in Gottlieb's group. But also there's been a lot of really nice work by Andreas and other people more recently on this type of thing. So that's the idea. You know, so again, so just to show that to convince ourselves that the system was working basically, we kind of warm up with some classical states, so looking at thermal states and coherent states. And again, just a slightly more detail, you know, what we measure are quadrature voltages. So we have just what comes out of our amplifier. We measure the I and Q quadrature. That's what we digitize. We then compute power, so a power time trace from our voltage times traces. And then from that, we can compute then the power-power correlation function. And if you kind of go through the full quantum calculation, you find that you can relate this power-power correlation to the G2 function this way. So it's basically 1 plus the power-power correlator. With the one trick or the caveat that our amplifiers have a significant amount of noise, and that has to be carefully calibrated and subtracted when we want to normalize the power-power correlator to get G2. But in the end, the point is that we can do that. So here I show the measured G2 function for 2 thermal states where we just change the measurement bandwidth. So that changes the width of the correlation function. So we get nicely a G2 of 2 at 0 delay. And then also the same thing for coherent states where we get nicely a G2 of 1 at 0 delay. So we see for our kind of canonical classical states that we get the right answer. And then we can do the same thing now for our non-classical states. So now we have our qubit, we bounce the weak probe signal off of it, and we look at the G2 function, and you see that we get this nice anti-bunching dip, which is what would be predicted from the theory. So we really show here that the signal reflected off of the qubit is non-classical. So again, I think this is really neat. We have this thing that can convert, this passive device that converts a coherent state into a non-classical signal. And one, I can make the point that, well, theoretically this should go all the way down to 0. We don't get there, but we understand that for technical reasons. Mostly it's just technical reasons, mainly that the bandwidth of our measurement device isn't sufficient. So you get kind of the G2 dip correlated with the measurement bandwidth. And that's because we have such strong coupling, basically. So our coupling is stronger than our measurement bandwidth. Anyways, we understand that. And, yeah. So that's the main result. But we can also look at the transmitted light. So we predict also for the transmitted light, because we suppress the one photon component, you predict that you should be able to see super bunching in the transmitted light. And we also see that. So super bunching meaning that at 0, we can get a G2 that exceeds 2. So these are some correlation functions at different probe power. And just looking at the 0, 1, we kind of see that. So for low probe power, we get the G2, which exceeds 2. So we see super bunching. And it's just that, again, as we drive harder, as the input state has less and less of the one photon component, what comes through is just the coherent state, and we don't affect the statistics at all. Right? So we see very nicely that this behaves the way that we expect, or the way that it was predicted. Okay? So that was the one experiment, or a couple experiments that we did with the atom in free space. And then, like others, we started thinking about, well, what's the next complicated thing that we can do? So Andreas showed you looking at 2 atoms in a transmission line. So we looked at a slightly different thing, which is basically 1 atom, but now sitting in front of a mirror. So we could kind of think about it, instead of 2 atoms interacting with each other, we want to look at the interaction between an atom and its mirror image. This is what it looks like experimentally. So how do you make a mirror in this type of circuit? Well, basically, I just terminate my transmission line. So in this case, I terminate, so this is my transmission line that's just kind of folded up. And then at one end, I terminate it with a short circuit, and that makes basically a mirror boundary condition. So the electric field or the voltage goes to 0. That's what a mirror does, right? And then on the other side, it's still a semi-infinite transmission line. And again, I put my qubit here, and I can kind of choose the distance in fabrication. So I could imagine putting the qubit at a field antinode or a field node. But one of the nice things that we get out of these superconducting systems, as Andreas mentioned, because we can tune the transition frequency of the qubit, we can actually tune essentially the effective distance of the system in situ. So as you measure in the number of wavelengths, we can actually tune the number of wavelengths between the atom and the system by tuning the qubit transition frequency. So that's one of the things that we want to look at. And then, as I said, the basic idea here was to look at how the interaction of the atom with the mirror or its own mirror image affects its coupling to the field. This is the basic data. So here we have, we're doing spectroscopy, so we're just measuring with a network analyzer, measuring the reflection as a function of an applied magnetic field. And we're just tuning the flux through our transmon. And you can see just the points where we see our qubit, and we get this kind of cosine tuning curve. But what you can see happens is that there's this region here. So here we see the qubit. But then there's this region here where the qubit disappears. So we don't see the qubit anymore. And if you kind of just put in the numbers, what you find is that this is basically the region at this frequency, 5.4 gigahertz. This is where you have 1/2 wavelength between the qubit and the magnetic and the mirror, right? So when I have half a wavelength between the qubit and the mirror, the qubit is sitting at an antinode of the probe field, and it decouples from the probe field, because of the classical interference of the signal directly scattered by the atom or emitted by the atom, and what's emitted bounces off the mirror and comes back, right? So I get classical decoupling. But what I can also look at is if I just take line cuts, say at this point and at that point, what I can also see is that the qubit line width is actually strongly modified, right? So this point, at this point, I have the line width that looks like this. So I have a fairly broad qubit line. And remember, essentially, the width of this line is the relaxation of the system into the transmission line. And then at this point where I'm kind of approaching the antinode, I see that the line width narrows substantially, and we get basically almost a ratio of 10 here between the line widths. So what's going on here is, as I said, we're seeing that the relaxation rate is strongly modified, which is interesting, because still remember that the qubit is in free space. We're not in a cavity. The qubit is looking directly into free space on one side, but still, as you can think about it as an interaction with its own mirror image, it's decoupling from the vacuum fluctuations. And we can actually be quantitative about that, right? So as we all know, so for t equals 0, or when the transition, or when the temperature is much less than the transition frequency is, which we are in this limit at our temperatures, you have that the relaxation rate should be directly proportional to the vacuum spectral density, right? So we can say that the relaxation rate, we have some coupling constant, k squared, times the vacuum spectral density at the qubit frequency. And what's interesting here, at least in this system, is that we can actually directly measure this coupling constant, right? So we have, as you saw, we have these very nice single atom or single photon saturation curves, and we can use that to kind of relatively precisely measure the coupling constant between the atom and the field. So we can quantitatively convert the measured relaxation rate to a vacuum spectral density. And here we show the results of that. So now I'm plotting the measured spectral density in units of quanta, h bar omega, or omega a, and now plotted as a function of the normalized distance between the qubit and the mirror, right? And so what you can see, first of all, the magnitude. So if you had the qubit in the open transmission line, what you would expect is the spectral density should be 1 photon, because I get half photon from each side. But what you can see here is that really, when we're approaching kind of this node, or the node of the field, we see that we very strongly suppress basically the strength of the vacuum fluctuations seen by the qubit. And we get to a minimum value here of 0.02 quanta. And just then this region is just the region where, it should actually go lower, but this is the region where we don't see anything because we decouple from the probe field also, right? So this, I think, is kind of neat. We can, and again, or just to make the point, this curve is not a fit. This is just a calculation of basically, 1 quanta times cosine squared, right? So we really see absolutely that we're measuring this vacuum fluctuation, and we can see that the interference effect of the atom with its mirror image suppresses the vacuum fluctuations that it sees by almost a factor of 50 from what you'd expect from the free space value. Okay. Okay. So that was one experiment. So another experiment, so the two experiments that I showed so far, what we were always looking at, we were just probing 2 levels of our qubit, right? So the interaction of a 2-level system with the field. But our systems are actually multi-level systems, as we've also heard. So we have, the transmon have a number of levels, and we can also then look at multi-level dynamics, or the interaction of the atom with multiple fields. So we can do, for instance, we can imagine having a probe beam which is resonant with like the 0-1 transition, and then we can add an additional tone, which we'll call the control, resonant with the 1-2 transition, and we can look at how those interact. And generally what we find is you get a power-dependent phase shift, which in the language of quantum optics is a CROSS-KERR effect. So I get an effective interaction between the probe and control, which is mediated by, in this case, my 3-level atom. And of course, we've heard about it already a little bit, but CROSS-KERR effect is something that's been proposed or talked about for a long time as a kind of interesting route towards photonic gates and QND photon detection and a lot of other interesting applications. So we looked at the CROSS-KERR effect in 2 different devices. So one is our qubit in a fully open transmission line where there's both reflection and transmission. But we also looked at one where and that has the problem that if we're just measuring one field, we're kind of losing half the quantum information. So to improve on that design, we made a design where our qubit actually sits at the end of a transmission line. So and in this case, we have an open circuit transmission, which enhances the voltage by a factor of 2 compared to the free space case. And then we collect all of the signal that comes back out, right? So we looked at these two cases. This is the data for one of them. But yeah, so as I said, what we're doing now is we have what we call our probe tone, which is kind of the weaker tone that's just on at the 0-1 transition, and then we apply a control tone resonant with the 1-2 transition, which we can find. And this is the data. So this is what I'm plotting here is the control-induced phase shift. So this is the difference between what we measure is the phase shift of this 0-1 transition, and then we look at the difference with the control on and the control off, right? So it's the control-induced phase shift. This is what it looks like. So here I'm turning up the control power, and I see that I get basically this increasing, a phase shift that increases in magnitude and is nicely symmetric. This is the color plot, and then down here I show 3 line cuts, which are these, and you can see that we can fit these. So say we actually fit all 3 of these curves at one time to just a simple 3-level atom model. And here for kind of for many photons in the control, we can get a phase shift as large as 30 degrees. But of course, we're interested in what this can be for kind of single photon level. So we basically can do the single photon level, but now because the phase shifts will be smaller, instead of just doing a continuous time measurement, we do a pulsed measurement. So we chop the control, and then we just look on a short time scale of the difference between the control and the probe, but it's the same basic idea. And this is what this is again the same data that we see. So this is the probe, the control-induced phase shift. So here, this is different probe powers, but say for an average number of photons in the control of 0.3, so you can see it's quite substantial. So this is all coherent states, even the control, so we can't say it's not single photons, but we can look at the average number of photons in a qubit lifetime, and we can make this plot now of, say, the induced phase shift versus the number of control photons. And basically for the 2 devices, for this device, we get a kind of initial slope of 10 degrees per photon, and here we get an initial slope of 20 degrees per photon. So you see that we get here, and actually I guess we'll probably hear some of the latest results from the atomic physics community, but at least at the time of this paper, this was kind of a couple orders of magnitude larger than what had been done for propagating states with real atoms. So I think this is something that's very interesting, and our theory collaborators have really looked at this. So like I said, one of the ideas would be to use this for single photon detection. So slightly different from Yasu's talk, where I think they have a kind of destructive photon detection. You could also think about doing quantum non-demolition detection of single photons. So our collaborators, and particularly Tom Stace groups, looked at this for a single transmon, and what they find is you get a signal-to-noise ratio of only about 1. So it's not horrible since you're detecting a single photon, but you kind of want better. But one of the interesting things is that because it's a QND measurement, I can actually cascade the measurement. So instead of just measuring with a single transmon, I can measure with one transmon, pass it on to the next one, measure again, and kind of do that in cascade. And by doing that, this is some master equation calculation where they really kind of look at how even the first detection can distort the temporal waveform and everything, but doing a full calculation, this is what they get, say, for instance, with 7 cascaded transmons, where you can really kind of clearly distinguish kind of 0 or 1 photon in the control. So I think maybe 7 is a bit more than we would want. But I think we're kind of working on ideas, say, for instance, you can measure with squeeze light or something like that, but I think it shows that kind of realistically this type of experiment is within reach. Okay. And so for the last part of my talk, how much time do I have? Okay, so fine. So I want to talk about efforts that we've been doing now at Waterloo So it's a collaboration between me and Adrian Lupascu, who's another professor doing superconducting qubits at Waterloo. And then the person really doing the work is a postdoc, Paul Foreign-Diaz. And then we've been working theoretically with Wan Ho, who'll speak after me, and also Borja again. But the idea here is, as we've seen in these superconducting systems, we can already get kind of strong coupling in free space between the atoms and the qubits, but we're basically wondering here just how far we can push that. And can we really push into what we would call kind of ultra-strong coupling, where the coupling is comparable to the bare frequency of the qubit. So what's the basic idea? So this is kind of preliminary work. It's not finished, but I just wanted to talk about it. But what's the basic idea? So here, everything that I've shown you so far in this talk was transmons coupled to open transmission lines. For this experiment, we actually want to look at flux qubits coupled to open transmission line. So a flux qubit is basically a superconducting loop with 3 or 4 tunnel junctions of varying sizes. And as was pioneered by the NEC group, if instead of trying to get coupling directly through the magnetic field, I can get strong coupling between the flux qubit and the transmission line by really embedding it in the transmission line, so that part of the loop of the flux qubit is shared with the transmission line. And this can give me strong coupling, kind of 10 megahertz coupling or something like that. But it kind of peters out there. But if I look in detail, what I find is basically the coupling of the qubit to the transmission line is determined by the superconducting phase drop across this line. And basically, the larger I can make the inductance of this little section of wire, the larger this phase drop will be. Right? So the game then is to try to figure out how to make this larger. And kind of the realization is that well, basically what's limiting the coupling here is I have, this arm which has all my junctions, and this has a very high inductance. And then I have this arm which is just a wire, and that has a very low inductance. And so all of the microwave current just goes through the low inductance part and skips all the junctions. So if we want to get to higher coupling, what we can do is just move one of the junctions over to this arm, and now there's no short circuit path for the microwave photons, or the microwave current. It has to go through some of the junctions, right? So this is the very simple idea, and this was explored theoretically by Borja and Wan Ho. And the idea is, this is kind of a plot from their paper. So here I plot the coupling G over omega. So G is the coupling constant, omega is the bare qubit frequency. And this is as a function of a parameter beta, which is just the ratio of the area of this junction to kind of the reference junction here. So the smaller I make this junction, the higher its inductance, the higher the coupling. And what I see, at least theoretically, is that by pushing this junction down, I should be able, at least theoretically, to really kind of push into this very high coupling regime, or this ultra-strong coupling regime. And so this is what we've been wanting to explore, or have been exploring. And I'll just make a comment here that if you go back, so this system maps kind of basically very precisely to kind of the what has been explored in the 80s as the spin boson model, or this was really by Leggett and et al. And an important thing to keep in mind there is that basically around this regime where I have G of omega kind of around 0.7 or something, there's actually a qualitative transition in the dynamics of the system where I go from essentially having what we would call a qubit, where I can have like Rabi oscillations or coherent dynamics, but I get a transition in the dynamics first to just incoherent tunneling, and then to actually full localization of the qubit dynamic. So it's just something to keep in mind that as we crank up the coupling, there's a qualitative, we expect, or in hindsight, a qualitative change in the dynamics of the system. So this is kind of what we see. So looking at a qubit now, so we can start something simple. Let's kind of pick a qubit with a beta of 4, where we should be kind of well away from this transition. And this is what we see. So we just see, again, here, in this case, it's, so here, this is magnetic field, which is tuning our qubit. We're just doing spectroscopy, and you see that basically we see this nice flux qubit tuning curve, and everything kind of looks normal. And we get a qubit line width here of about 75 megahertz, which is comparable to what we've done with transmons, I think more than other flux qubits. But so big, but it's still just a qubit. But let's see what happens if we go further. So now we look at something where now I jump from 4 to kind of 1.2 here. So now we're kind of deep in the region where I expect to be, a change in the dynamics. And what do we see? Well, in fact, we see something completely different. So basically, it's the same thing, the flux versus the spectroscopy. But now I see basically a central feature that has almost no frequency dependence, and I see some satellite peaks here, and basically the qubit is gone. And also, just to make a point, this scale is completely different from the last one. So if I superimpose the data from the last one on top, you can see that this central feature basically is in the range of flux of the entire qubit spectrum here. So when we kind of push to this, what should be very strong coupling, we see something that's really very different. And we're trying to understand now if maybe this is kind of a signature of maybe moving into this qualitatively different regime. And just a couple more, so I said here, whoops, I was building, okay, this is our qubit, so just a few more details of what we're seeing in this regime. So I said if we kind of look as a function of frequency, say fix the magnetic field and look as a function of frequency, we see kind of a featureless spectrum. But if we do the converse, which is fix the probe frequency and scan the magnetic field, we actually see kind of a nice kind of line shape. So we see something that's reminiscent, you would think of ESR, where say I have a fixed, I have a cavity that I'm measuring with, so I have to fix my frequency, and then I change my magnetic field and tune the transition through that. So kind of curiously, we see this nice line shape. These are the satellite peaks. We see this nice line shape in magnetic field, and we see that if we crank up the probe power, that it saturates in the way we would expect for a kind of two-level system. And we can also see that if we do pump probe spectroscopy, so in addition to our weak probe, we now put in a strong pump at another frequency. We see that our one line that we see in magnetic field now splits into two lines with a splitting that's linear in the pump amplitude. So again, this is kind of reminiscent of a two-level system, although, as we said, if we look just in frequency space, we don't really see a nice resonance. So I don't know, there's something interesting going on here. We don't fully understand it, but we think that it might be kind of the signature of this transition to the different dynamics, and we're trying to understand that or really see if we can explain it in that context. But I think, and what we're doing now also is understanding this regime, but also basically we can do measurements where now we try to fabricate devices with different betas, and we're trying to get close to that transition region so we can kind of really see, crank up the coupling, see stronger coupling, but see if we can really understand what's going on in this transition between these two regions. Okay, so that's my talk.
Okay. Questions? Yeah.
So what would happen if you put the same type of flux qubit coupled to instead of 1D waveguide, but the transmission line resonator?
Right. I guess we should be able to start to see ultra-strong coupling effects and things like that. I guess it's been a little bit. This in particular was a collaboration between Adrian and I. So his part was the flux qubit, my part's the 1D. So that's what we focused on. But I guess we could also do the same thing and start to look at some of these kind of ultra strong coupling effects in for cavities.
So the difference would be either discretized mode or
exactly
mode.
Right.
And for the discretized mode, you do not discuss something like the incoherent regime?
Would there be? I would have to think about it. Okay, yeah. No, then you have like the quantum Rabi model and things like that, and a little bit, So it's just very different, right? To couple to a continuum and to couple to the transition. Basically where the transition happens is when the line width of the qubit is comparable to the, line spacing of the qubit, right? And so then I have I just have a qualitatively different dynamics, which at least is kind of understood Again, this is what was studied in the 80s by Leggett and everything like that. But we kind of have a nice toolkit to kind of look at that in kind of more detail now.
I was wondering whether you could replace one of your junctions in this last experiment with another squid loop and then sort of tune continuously between these different regimes. Is that possible?
Yes and no. So I think we're actually going to start doing some things like that. So I think it's very difficult to tune continuously. And that's because the flux qubit basically tunes, so the entire flux qubit hyperbola is kind of, has a width of like a milli-phi naught. Where then if I made a squid loop to tune my coupling, that's tuning on a level of a phi naught, right? So I would need to be able to somehow, if I want to flux tune those two loops, I need to be able to cancel the mutual inductances to like a part per 10,000 or something like that, which I think is very difficult to do. I think what we're going to try to do is, what we could do instead is, in a sense, sample the coupling, right? So we could make the flux qubit tune, we could make the flux qubit loop really big, and the tuning loop small, and then kind of sample kind of many points of coupling, in a single device. And I think that's one thing we're going to try to do.
Can you elaborate a little bit on how you reach this regime? Because for transmons, I thought, or for just kind of normal transmission line, there was this limit of fine structure constant, right?
Right.
There's G or omega.
Right.
Right. So what is like? What's the idea? How is it? How do you circumvent this limit?
I know, do you have a comment on that one?
So these different physics. The transmon is based on the dipolar coupling between these big two charges separated from each other. Here the current is going through the qubit. And the current moving through the qubit can alter the energy levels of the qubit itself very deeply.
Yeah. So I guess in some sense it's not, this limit of the fine structure constant comes from having a kind of electromagnetic coupling. So I have a separate qubit and I have a transmission line and I'm coupling through electromagnetic fields. Here we're not doing that. It's not a mutual inductance coupling. We're really directly injecting the microwave current into the junctions of the flux qubit. So I think it's maybe in that sense that we kind of circumvent this electromagnetic limit.
The properties of the transmission line is like the group, the phase velocity is still basically speed of light and everything. Right?
Yeah. But yeah, the microwave currents, so our plasma excitations are really getting funneled really through the qubit. So I think it just interacts much more strongly.
It's a different degree of freedom you're coupling to.
Right. Okay. Yeah.
Helmut?
The first part of the talk, I remember that if you have an inverted system, it's a sort of an ideal quantum noise detector, and
right.
nicely demonstrated this here. I remember there was another debate in optics about excess noise. So the question, if you have an unstable resonator or a resonator with decay, should the enhanced quantum noise present?
Okay.
Is there a way to measure this in these systems? I think the debate was never really solved in optics. I don't remember everything, but there were different people claiming different things.
Okay. I'd be interested to hear about that. So I do think this is kind of, this idea of using the qubit as a kind of a quantum spectrum analyzer is not our idea. Other people have done it or proposed it, but I think it is kind of very much a general tool so that we can do that. So you can use this to probe kind of, the vacuum noise density or whatever noise density you have. So I think it's a general thing. But yeah, if there's some unanswered questions, I'd be interesting to hear about them.
But I have an objection.
Okay.
That relates to Helmut's point.
Yeah.
This vacuum and probing the noise in the vacuum, what you're probing is the structure of Helmut, solution to Helmut's equation.
Sure.
Right? And that's completely different than the vacuum. You separate Maxwell's equations in QED into the classical parts of the solution of Helmut's equation. And the quantum part is the amplitudes that occupy those modes.
Right.
So to say the mode density goes to zero, the vacuum noise goes to zero, is a statement of the classical character of electrodynamics. And the stuff that Helmut's talking about is that if you solve Tony Sigmund is the pioneer of that. If you solve Helmut's equations in open systems, normally we take a cavity, we close it, we pretend that it's completely closed, and you can solve these perfect modes, then we add a little bit of leakage. The modes are power diagonal, right? So they're orthogonal. And what Sigmund pioneered is they're not.
Okay.
And so you can't sum up the power as, psi 1 squared plus psi 2 squared, the coefficient. So that investigation that Sigmund looked at for spontaneous emission in lasers, for example, spontaneous emission, is really a question of the character of modes of open systems.
Okay.
And to say that it's somehow quantum,
Right.
yeah, quantum inhabits those solutions of the
Sure.
spatial part-of-Maxwell's equations in different kind of circumstances.
Right. Yeah, no, I mean, I completely agree that all of the modes, which I think is generally the case, comes from solutions of Maxwell's equations, and the vacuum part is the operators and how things are occupied. So I agree with that. But yeah, if there's some sense of, if there's open questions of if there are excess noise, and perhaps we could measure it with a qubit, I mean, that's interesting.
There was some open question in terms of the G2 measurement to the closed cavities which are not perfectly closed, which then lead to shifts which were really important for these guys. I mean, they're really trying to suppress the real vacuum fluctuations at the position of the electron, and I think there must be a relation, but I don't see it immediately here with the material. I agree it's different, and maybe the models have to be refined. But
Okay, with this, let's
Okay.
thank Chris.